you. Thanks for having me, and thanks for coming to my talk. So I'm going to be talking about, yes, these new degrees, punctual degrees. So I'll introduce all of this. This is in the setting of computable structure theory. So I'm going to use some examples of the rationals as a field to hopefully maybe try to get more people interested in this. And really, hopefully, I'll show that this area is interesting and motivate it, and I'll introduce everything, so don't worry. And mainly, I'll focus on some new work that I'm currently doing within the punctual degrees, but this extends my PhD thesis that I did in Wellington with Sasha Melnikov and Dan Turetsky. So we'll get started, and first, of course, I'll put up definition for computable presentations and computable isomorphisms to make sure we're all on the same page. So our computable presentations, right, is where we have so we're only going to be looking at countable structures because our domain is going to be some computable subset of the naturals. And then all the functions and relations in the language are going to be computable. So for people not used to this, I would say, like, imagine your structures kind of slowly appearing as you're doing these computations rather than having everything at once. And of course, we want this notion of isomorphisms and sameness. And in this case, we're going to be looking at computable isomorphisms. Right, so looking at two presentations, of course, as structures, they're going to be isomorphic, but then we're asking whether there's a computable isomorphism, right? Because the structures are the presentations are, have domain natural numbers, so you're looking at functions from the natural numbers to the natural numbers. Okay, so a common thing to think about, right, is going to be computable categoricity. And this is where we have exactly one computable presentation up to computable isomorphism. Okay, and I want to start with an example, which will then motivate what we're going to talk about. So this is where I made a nice example with a field. So we have, so remember we're kind of coding the rationals into the natural numbers, and then we have that our addition and multiplication is computable. And from that, in fact, we're going to get our subtraction and division and our 0 and our 1, right, being computable. So why is it computably categorical? When you're kind of imagining two presentations of this structure, now really it's all about, so you can fix the first element, right? You can look for where your 1 is, and then you're going to map these together, and then any other natural number, eventually it's going to be n over m for some n and m. So you can just kind of wait to find what this is, right? By adding 1 many times, you've got your subtraction in case it's negative, have your division to find the inverse, right? So you're just kind of like, everything's going to look like n over m, so wait to find out what it looks like, and then map it, okay? But this very, very heavily uses our unbounded search, right? It's like, well, we have no idea what n and m might be or any bounds on this. It's like you really are having to wait for these to show up. So really what the focus for this talk is going to be is what happens if we now forbid the use of unbounded search. Okay, and nicely, like, there is a nice notion of this, right? So for people who've heard of primitive recursion, this is exactly computable without unbounded search. So we will come to our central kind of definition of the presentations we're going to be looking at. So this was first introduced, reasonably recently. I guess it's heading towards almost 10 years ago, but it still feels somewhat recent. So we're going to be talking about punctual presentations. And so now our domain is the natural numbers, or an initial segment in the finite case. And now our function relations are going to be primitive recursive. So one thing I want to point out straight away is that our domain, notice that I'm not saying a primitive recursive subset of the naturals, right? This is, in the computable case, we use the computable subset of the naturals, but now really, so this was considered before, like primitive recursive presentations, and that's why it's not called primitive recursive presentation. But if you allow a primitive recursive domain, then you're sort of allowing some unbounded search to be kind of hidden in how the domain grows. But really, we want, for our presentations, what I want you to imagine is now we have, again, our structure is appearing, but it's now having to appear fast, right? It can't just like wait before it finally adds another element and tells you where it is. So that is why, right, we have the whole of the naturals. So we don't allow any of this delay being hidden away somewhere.
How is that so much different from, I mean, if you allowed one of your relations to be a unary relation that calculated that was true on a primitive recursive subset, you would be able to encode the same things in that?
I mean, no, because like a primitive recursive relation is just going to tell you yes or no quickly, but you don't know when the next yes is. You know, so like things can still be weird with the, like especially the relations kind of make things strange, and it can sort of delay relations sort of in that way by saying these aren't related for ages and then finally there's something new. Yeah. But the structure itself is going to be appearing quickly, so at least it has to tell you whether these things are related or not, like quickly. Yeah, okay, so now we want to know that some of these exist, right? And so in some classes, in some natural classes, we have that every computable one has a punctual presentation. So this is like linear orders, Boolean algebras, torsion-free Abelian groups, and some of these, but also we don't always have this, right? So in some natural classes like undirected graphs and torsion Abelian groups, we have that there is a computable one that is not punctually presentable, right? So at least I put this up to kind of motivate that at least we're not looking at the same class of structures, right? And this is where if you allow primitive recursive domain, you do get the same class of structures. So that's sort of why that's important. Okay, just to motivate it a bit further, I want to vaguely mention polynomial time presentations, right? So this is all in the realm of feasible computation and wanting things to like happen somewhat quickly. Polynomial time, of course, we have bounds, but they might not be polynomial time. But this is nice because in lots of cases, sort of once you remove the need for unbounded search, sometimes it might just be polynomial time for free, right? So in some of these cases, so I'm saying for free, you know, it might not be, but in lots of these cases, it does sort of just like turn out to be. And of course, in the case that you show that there's no punctual presentation, then you can say there's no polynomial time presentation. So it's somewhat relevant to these sorts of things, but it's really nice to work with because primitive recursion is very robust and kind of a nice, solid definition. Rather than working with polynomial time stuff, you're kind of having to, it's very notation dependent, and there's actually lots of not quite equivalent definitions. So that's sort of why we focus on this, but I wanted to point out this relation between these. Okay, so now, of course, we want our like equivalent version of punctual categoricity. And so, okay, so we're going to say it has a unique punctual presentation up to something, right? So you're probably, the first guess is going to be up to primitive recursive isomorphism, but the inverse of a primitive recursive function might not be primitive recursive, right? So that's not going to quite give us what we want. So instead, what we use are these punctual isomorphisms, where you have, if you have an isomorphism and both it and its inverse is primitive recursive. And this is sort of our notion of, right, like our sameness. So we can go back and forth, exactly. Okay, so an example. So, I mean, basically, as we talked about, right, the fact that the way that this was computably categorical really heavily relied on the unbounded search, right? And really, like, how you actually show that it's not punctually categorical is you're going to you can have some standard copy that really, like, comes through and generates from the element 1 as expected. But now you can have another version which can sort of add elements that eventually it's going to look like n over m, but I'm not going to tell you for a very, very long time, right? And I can basically do a normal sort of diagonalization. I'm listing out all the primitive recursive functions, and I can one at a time show that this is not going to be an isomorphism by delaying this section for long enough, right? And then I connect it once I diagonalize and I repeat. Right, so this is not going to be punctually categorical.
For that method, how do you make sure that the operations are...
Well, because I just need to show that, I mean, I can still show that I can do, like, I can keep generating this section, right? But I'm just not saying how it's exactly connected, right? Like, I can keep, like, adding and multiplying all these numbers, but I just kind of delay ever actually telling you exactly where it is. Yeah. Yeah.
Even if you just have your connecting to all the operations and everything, just looking at the rational plus less than, it's already not punctually categorical.
Yeah. Yes.
So then it's not with the delay, you're putting it somewhere.
Yes. Yeah, but I think, I mean, you're sort of delaying how it's kind of connected to everything yet. So you're kind of growing like a whole new section over here. I think that's sort of how it works. Rather than, you also get this with the rationals as an order, but for this you're sort of, you're just delaying an element showing up in an interval. So I don't think that same method works for this because you'll need the other operations. Yeah. Honestly, like, I'm very open to, I should have put a mild question mark to this because this is thought of recently. I think that this is true. However, perhaps there is a way in which it is not. But at least it's clearly, it seems like you should be able to do it somehow.
If you did it without division?
Yeah, maybe me adding division, did me adding division ruin things?
I mean, it says all of the whole ring Z maybe would appear quickly, but you could delay putting in 1/2.
Yeah.
Things like that. Because if you don't have division, they aren't generated.
Yeah, maybe I did ruin it by putting in division. I thought like, oh, like it doesn't help, but maybe it does, because that's the other thing, right? In the computable case, just having addition and multiplication, right? Like, you just need those to be computable and then you get everything else. But in this setting, like, you wouldn't, right? Like, because those all require unbounded search themselves. So maybe, I mean, I could have just made this example like the rationals and you just have addition and multiplication, and then it clearly doesn't work for other reasons. But I thought it didn't even work for this, but you know what? I'm open to suggestions about whether this is fully correct. Okay, but examples that are definitely true, because they're actually proven, while this was just me vague. The example was me kind of thinking about it, and there is no proof written. Basically for some classes like linear orders and Boolean algebras, they're punctually categorical if and only if they are finite. So it's very hard to get, like, you basically, it's very easy to break punctual categoricity in this way. And I don't want you to think they're only finite ones, and that's why I put an example of an equivalent structure where, of course, it's kind of long, but again, it's nice. I put the whole thing because it's an if and only if, and that's nice. But these ones, you can actually get an infinite structure that is punctually categorical, right? So it's not just the infiniteness that's breaking it. So, I mean, immediately an open question is here, especially because, like, now I'm more confused about the field, right, as whether there's a characterization for when these are punctually categorical or not, right? This hasn't been done at all. And same for rings. Yeah, I should have just done the ring example. It was much easier, but then I then I thought this example was nice, but maybe it's not, so we'll see. Okay, so those are our examples of punctual categoricity. Okay, so generally, like, when we looked at the examples before, like, all of the punctually categorical stuff was, like, really, really simple, right? It was finite, or even in the equivalence one, it's still very, very simple, right? So you might be kind of thinking then probably every punctually categorical structure is going to be computably categorical. And somewhat surprisingly, this is not true. Okay, and so there does in fact exist a punctually categorical structure which is not computably categorical. And in fact, it is even, I don't know, worse or better, depending on your perspective, that in fact there is a punctually categorical one which is not even delta 1, categorical. So basically you can really make these as complicated as possible in the computable sense. So this sort of motivates, like, this is an interesting thing to think about, like, in itself, right? It's not just, it's somewhat surprisingly, of course it's linked to, like, computable structures, but there's kind of an interesting separation between them, right? Okay, so now I want to talk about the punctual degrees. So, of course, we threw away our primitive recursive isomorphisms because we wanted the equivalence for our punctual categoricity. But, of course, the primitive recursive isomorphisms are actually very nice because they're actually giving us a reduction, right, on the collections of presentations of a structure. So now we can think, like, of this as a reduction, which is pretty cool, and I feel like as computability theorists, this is cool because we like degree structures. So now we get our degree structure. So we look at the collection of all punctual presentations of a fixed structure. And now we're going to be looking at this reduction if there exists a primitive recursive isomorphism from one to the other, right? And then we're thinking of the punctual degrees, right, modded out by this equivalence. And so what I want to, like, point out here is that, right, this is a degree structure, like, for each structure. Like, you fix the structure, and then this has a punctual degrees, right? It's not like just one punctual degrees that I'm thinking about, but I'm thinking about the punctual degrees of various different structures, right? So this means there's, like, heaps of things to possibly look into, right? Because you can kind of look into what's going on in the punctual degrees for various different structures. So, to give an example of what this can kind of show is that the punctual degrees of these three structures, so we have the dense linear order, the random graph, and the universal countable abelian P group, are pairwise non-isomorphic. And I think this was somewhat surprising because they use very similar back and forth arguments. But that's kind of showing that maybe looking into this exact structure is kind of telling you something about the way the unbounded search is really being used. Because while the proofs look similar, clearly something's going on. And these are all for various structural reasons, so I put them here. So for example, we know that the punctual degrees of the dense linear order has a greatest degree, so everything embeds into some maximum thing that's basically just growing fast everywhere. And it's also downwards dense. And meanwhile, we know that the punctual degrees of the random graph does not have a maximum degree, but it does have a maximal degree. So it's not upwards dense, but it doesn't have a maximum. And then lastly, the abelian P group is upwards dense. Yeah? Like below, like there's something below anything.
Everything has something below it?
Yes, exactly. No minimal element, you could also say it like that. Yeah. Yeah? Yeah?
So when you say the primitive recursive isomorphism, you mean the forward direction primitive recursive only and not the backward one, right?
Yeah, like to get a strict, like this is strictly above this thing, I want a primitive recursive isomorphism one way, but not the other way. Yeah, yeah. So that's how I'll get things that are strictly different. Higher up is the thing that's onto, like it goes up, like the isomorphisms go up. Maybe, yeah, up. I just think up. Yeah. Okay, so clearly there's something interesting, I would say. Hopefully people now feel like there's something interesting to look into about these degrees, right? It's giving us something. So, okay, well, so now, okay, so this certainly has a minimal degree. Hopefully it has more than one degree because now the punctual categoricity is up for question. But let's suppose that I'm not completely wrong about this. I mean, this is true for every finitely generated structure. It's going to have a minimum degree because it's kind of just the standard copy that's generating from its generators. And you can always embed this up because you can just sort of non-uniformly fix the generators. And then you can do the mapping, right? So even if it introduced something weird on the side, you don't actually need to introduce that until the bottom structure, right, gets these things. So that's sort of why the kind of standard copy for finitely generated structures has this minimum element. Okay, and what I also wanted to say was that, is that it's dense. If in fact, again, this is true for finitely generated structures. And so as long as it has more, well, even if it has one degree, it's still true. So generally, this statement is technically true. Whether there's the A with A and B, maybe perhaps is up for question. But anyway, so I just wanted to give the vague idea because I'm going to talk about density a bit more. So basically, to show that it's dense, right, we're going to take two things, one above the other, and build something between them. And sort of the idea is that you're swapping between like copying like A or copying B, right? So to diagonalize from B to C, you're going to basically wait for it to show you where it puts the generator, and then obviously if it puts it in the wrong place, then you're done, so you can move on, and otherwise you kind of are copying A, and since there's no isomorphism from B onto A, you can kind of wait and see that it maps it to the wrong place. And then for the other one, you're kind of doing the same thing. So it's really, it's about like swapping between which one you're copying. However, you need to do this in somewhat of a smart way. You need to know when you really have diagonalized to move on. And again, I want to point out that another thing that is maybe a bit different for computability theorists, like normal computability theorists, is that when we diagonalize now, our functions are all total. And so we could actually just wait for it to hold, and then we can diagonalize, right? So that kind of gives us something extra, right?
This argument for proving density,
Yeah.
what is special about this structure that you're using?
I guess I'm, no, we're going to eventually see, the spoiler is that not everything is dense. I guess the thing is that because it is a rigid structure, you can tell as soon as, like, you can tell when you've diagonalized. You can tell once this map's there, then it's definitely not an isomorphism. So now you know I can move on. And like, I've successfully diagonalized. So it's kind of about knowing whether you have diagonalized or not, right? Kind of knowing whether this PE is an isomorphism or not. So in cases that we can sort of see this, then we can kind of do this density. which we'll see certainly more about very soon. So I can expand on that. But so here's some more examples of things with dense punctual degrees. So we have the finitely generated things, which is sort of what I was saying before, right? So for anything finitely generated, you can do this. We've also got anything rigid and also anything computably almost rigid. This is sort of like if you have an isomorphism from A to B, and then you have a computable function that tells you exactly where everything else is going to go from that. Anyway, that's just vague, but these are just some examples. And then we have the integers, but then more recently we have the integers kind of multiplied by any finite number. But we still don't know if like the integers multiplied by omega is dense or not.
Sorry, what is zeta?
Zeta, sorry, I wrote it up here. Zeta is the integers as a linear order. It's just because I didn't want to have to write something weird. Yeah.
And the data times n is like a concatenation?
Yeah, well, like you're putting copies. Yeah, n copies of the integers, yeah. Yeah. Yeah, n of the integers. Yeah, yeah. I'm pretty, yeah, now I think so. Is it written the wrong way?
What is the structure in the last line?
Yeah. It's
It's just a concatenation of n copies of z as an order.
yeah, right? Yeah. Thank you. I always get worried about the order of these things, so I'm just Yeah. Okay, great. As a linear order, right? So it's just like n copies of the integers. Okay. Thank you. Okay, so this is a few examples of things that are dense, and then of course the spoiler is that not everything is dense. And in fact, the dense linear order, the punctual degrees of the dense linear order is not dense, which was somewhat surprising, and it's a very, very long paper. But moreover now, like a bit more recently, we have that there is so now again zeta is the integers, and we have this discrete linear order. So it's not necessarily the density of the rationals that's doing it. There's something else going on. That's why I put that other example there. And we at least have one characterization one full characterization for the density of punctual degrees, and that is for equivalence structures. I didn't bother writing it here because it's kind of long, and you can look it up, but I just wanted to point out that they have been characterized at least in one natural structure so equivalent structures have some are dense, some are not dense, and this has been characterized based on the sizes of equivalence classes, etc. And there's some nice property that I can never remember. Okay.
And the second theorem is the same as n cross z with lexicographic order? Is that what that is?
I don't, no.
Does it mean it's a countable number of copies of z concatenated? Is that what this means? What?
It's just z times z.
Yeah, zeta squared is z times z.
Oh, okay.
Yeah, but then you're adding all of these, right? Yeah. But then you're adding all these different ones up, so it's a bit messy, but it works. Okay, so what I want to get to is, basically we're heading for recently with H.T. Ko, who recently started his postdoc in China. We found a sufficient condition for density, and these are the definitions we need to get there. Okay, so we're looking at this computable automorphism sort of group where we have the indices for this is the collection of automorphisms for a fixed punctual structure. So we're fixing, right, a presentation of a structure, and then we're looking about the index set of the automorphisms of that structure. Okay, and then we kind of want to say, right, that we can, it's listed by something if we have representatives for each of these, right? Because for people who are familiar with computability theory, right, because of padding and stuff, like, right, you have a bunch of indices for each function, so you just need like sort of a witness for each of these automorphisms, right? So that's what we mean by listed. And then we're going to kind of be looking at the complexity of this listing, right? So we're looking at how complicated this listing set is. Okay, and this kind of comes back to why we're looking at this, like sort of as what I said, it's all about when we're doing the swapping thing for density, it's about how do you know that if I've successfully diagonalized or not, right? Like, is this an isomorphism or not? So this set is sort of helping me in this way, right? There's some way to identify when things are actually going to be isomorphisms or not, in some sense. Okay, so just a couple facts. Okay, so for any punctual structure A, this set is clearly going to be pi 0, 2, right? Because we can just check if everything's preserved and then check that it's onto. And additionally, you have that, oh damn, I just copied the same thing, that's a typo. Okay, well clearly the statement I wrote is correct. But what I wanted to say is that sigma n plus 1 is the same as pi n. So basically, the reason for me saying this is that, right, your kind of three options for your punctual structures is going to be you have pi 0, pi 1, pi 2, right? Or equivalently, sigma 1, 0, sigma 2, sigma 3. Okay, yeah. Okay, so those are sort of the options for these computable automorphisms groups, and then let me give you the theorem, which is, okay, so immediately I put finite language and I put a star against it. We kind of think it probably works also for an infinite language, but the way we actually prove it, we use another result for sort of a punctual universal structure that relies on finite language. And that's why it would be very messy, I think, to prove for infinite languages. So that's why the star's there. Okay, and basically what you have, right, is you have some punctual structure, and then you need to know that every punctual presentation of that structure, you have that this computable automorphism set is sigma 0, 2 effectively listed, or equivalently pi 0, 1 effectively listed. And that's when you have dense punctual degrees. Okay, so we at least have some sort of sufficient condition. And so immediately, I guess we say that it's not a characterization. So it's not necessary. So there is something that has dense punctual degrees, but it's not sigma 0, 2 effectively listed. So unfortunately, we do know that we haven't got the whole thing, but at least we have something. So I think it's still a very, very nice result. And just to mention that this example is basically, when we talked about punctually categorical things, we had that this equivalence relation, the one with equivalent structure that has only classes of size 1 is punctually categorical, so it's somewhat trivially dense, the punctual degrees, and in this case, it's not sigma 0, 2 effectively listed. So, but still, so I don't mean to like put a nice result and then immediately try to say that it's not so nice, but I still think it's very nice. But, and so far, all the non-density proofs are like so complicated and so long that honestly, it would have been more surprising if this did actually work as a characterization, or even finding a sufficient condition for non-density looks very, very difficult. Okay, and so, so I wanted to give an example. Okay, so first of all, we want to show that this was useful to give us something. And so when we had that slide about dense punctual degrees, we can use our theorem to sort of get all of these results, right? Of course, except for when we talk about equivalent structures, because that clearly doesn't work for those. So I wanted to do an example, just sort of like how we're kind of checking if this computable automorphism set is sigma 0, the complexity of the set. In this case, it's sigma 0, 1, so it's not actually the top level that's possible for dense punctual degrees. But just to give an example, really what you're doing is you can non-uniformly fix the generators, and then you can sort of for each phi e, you can test whether it eventually generates, whether when you apply it, if it eventually generates this set of generators that you've fixed, and then you would know that it's a computable automorphism. So then it's CE, right? You're just sort of like waiting and checking. So that's just a vague idea on how we can sort of use this, and then we would know that, now we know that all the finitely generated punctual degrees, the punctual degrees of all finitely generated punctual structures is dense, right? Which we did already know, but now we've done it in a different way, right? Okay, and we have some new examples that weren't done before, and these all come from just directly using our results. So not only can we reproduce the things that exist, but we've got some things that are new about it. Okay. So, I mean, I don't necessarily want to talk through all these examples, I'm just showing you that they exist. Okay, so from here, I'm going to talk a little bit about some other structural aspects of the punctual degrees. So I'm going to move from density into embedding lattices. Okay, so a task that Sasha gave me in my PhD was to look at embedding the atomless Boolean algebra into the dense linear order, into the punctual degrees of the dense linear order. Right. And so why do we care about that? That's because we can embed any distributive lattice into the atomless Boolean algebra, right? So embedding distributive lattices, we would like to know if we can do this. Right, and that's where you're preserving the supremum and infimum. And so as part of my thesis with one of Sasha's other PhD students, we did somewhat of a small step towards this, right? So this is that we can embed the diamond lattice, right? The very, very first step. So we can, right, and remember the punctual degrees of the dense linear order is very complicated, right? Because this is one of the examples where the punctual degrees are not dense. So clearly there is something weird going on with them. And that's somewhat because of that, it's not so surprising that this is really difficult as well, right? And so, yes, what we can do is at least we can embed the diamond, so that's nice. But it was very hard to push this further, and the strategy itself didn't just naturally, right? Your hope is that you can do the diamond and then naturally you can just do everything else, and unfortunately that certainly did not work. So then we decided that was hard, and so then we did rigid linear orders because the rationals was being too difficult and we wanted to check we could do it for those. And in this case, this works really nicely, right? Because really the difficulty is kind of piecing together the isomorphisms to show that the supremum and infimum are preserved. And so when you have rigid linear orders, now they piece together nicely, right? So you take away all the difficulty from the dense linear order. And in fact, we can do something quite nice in this case, right? We can actually embed the atomless Boolean algebra between any pair of things. So at least we know this about rigid linear orders. So, but we do have like a bit more than that, as you can see from the empty space. So we do have the integers, so that's nice. The second condition looks complicated, but basically we're saying if we can split into 3 computable parts, which is the same as them being punctual, if you basically have some sort of rigid part in it, that's sort of rigid within the whole thing, then we can also kind of apply our construction there. So we can, in fact, do things like omega plus the rationals, right? So because we can just ignore the rationals and not mess with it and just do our construction on the nice bit. So at least we have something that sort of involves the rationals. Okay, but luckily, very recently, I've been working with HG Co and also Leland Co on trying to push the dense linear order one further. And so I've put these all as conjectures, like because we're starting to have methods, we think we can maybe do some of these things, but certainly no proof is fully written, and so I do not want to call them theorems yet. So, I mean, what can we do? One is that not only can we, so I mentioned at some point that there's a maximum degree for the dense linear order, and so we can embed the diamond there, like at the top degree, and in fact, we can actually do the 8-element Boolean algebra at the top degree, but once again, that doesn't seem like it can be pushed any further. But that's like where, right now, I don't have full control over all the copies, right? Like I'm fixing the top copy. So now, very recently, last week, we came up with a new strategy for the animalist Boolean algebra, and it seems very promising. But this one is a very weak, I mean, I still hope that we can do it. So in that way, it's still a fine conjecture, but it's whether we've got there or not. And I think we're very close now. So that's exciting because I was very stuck on it for a long time. And in fact, actually, we also think we can embed a non-distributive lattice. We think we can do the pentagon lattice in 5. So, you know, we're building up some more interesting things about the punctual degrees of specifically this structure, mostly because, right, it's got a lot of strange properties so far, and this is why we continue looking at this one. So those are some cool, you know, I wouldn't call them results yet, hopeful soon results that will exist. N5, where is, oh, yeah, it's the one that it looks like this. So it's sort of got these elements. Can people see that? Yeah, it's a pentagon. I feel like I drew it really badly, but it's a pentagon. It's non-distributive, which is the interesting part. And this is one of the classic non-distributive lattices that people try with. Sorry? This one? Yeah, I think so. Yeah. Okay, so those are our lattices that we're working on, right? And again, like you can see that there's many more questions that can be asked in this realm as well. I mean, so far we've only looked at linear orders here. There is a paper looking at embedding lattices for finitely generated structures. So there's some results that way. But I think those are the only ones that exist so far. Basically, this stuff on linear orders and finitely generated structures. So there's clearly a lot of things that can be done. So I will advertise that. Okay, so now I want to move on to a little bit about computable dimension. And of course, eventually, not surprisingly, we'll talk about punctual dimension. Okay, so computable dimension, right, is going to be where you look at the number of computable presentations up to computable isomorphism. So you have the computably categorical ones, or the dimension 1. And then I guess this was kind of initially looked into because the natural structures that people first were coming along seem to always have kind of dimension 1 or infinity. But Goncharov did show in like the 1980s that you can show that there is a structure of computable dimension n for any n. So you can get, so of course this was first, he built by hand a structure of computable dimension 2, and then the case for above 2, he just kind of joins the structure together in some way, right? You're kind of imagining like 2 copies of the structure together. So those kind of just followed naturally. So of course we're going to think about punctual dimension, and unsurprisingly the definition is as expected, the number of punctual presentations up to punctual isomorphism, and then in this case we can also get all of these structures. So this was first done by Sasha and Selwyn, that they showed that there's a structure of punctual dimension 2, and then part of my thesis, I mean, one of the main points is that you actually can't do it by the same trick that Goncharov did. The trick that Goncharov used is provably you just get dimension 1 or infinity, and so it doesn't work, and so we do actually build them by hand, and so so we know that we have all of these, but again, it kind of uses a different technique. And the techniques generally between computable and punctual dimension are very, very different as well. You can't just take a computable dimension proof and sort of adapt it. It's quite different. Additionally, just to kind of get more of a picture of what, trying to think about these punctual dimension results, but more in the framework of the punctual degrees. What we can do, right, is you can kind of extend the technique, and you can in fact get computable dimension, oh, that's not supposed to be computable. That's definitely supposed to be punctual. So that's a typo. Punctual dimension infinity, and you get a anti-chain in the punctual degree. So you've just got infinitely many copies, and it's exactly that. It's not just like that exists somewhere, but the only degrees are all incomparable with each other. And in fact, more recently, it was shown that if you have finite punctual dimension, then they have to be an anti-chain, right? So the ones, all of the punctual dimension n above, they are exactly like completely separate degrees, right? And it kind of comes from this density is quite hard to work with. So having one above the other and nothing in between, it doesn't quite, yeah, well, it doesn't work. I mean, and now it's provably that doesn't work. Yes, okay. So to kind of put forward, oh, I feel like my slides got out of order because I feel like I had another slide at some point. Maybe we'll come back to it with some open questions, but even if that comes up at the end, that's still okay. So let's move on quickly. I mean, I don't have heaps of time, but I just at least want to mention it, and of course, if people are interested, you can talk to me more about it. So I just want to point out this fact that the actual like equivalence class under this reduction is not the same as the punctual isomorphisms that we were talking about, right? So to be in the same degree, we just need a primitive recursive isomorphism in each direction. But to be punctually isomorphic, we need one isomorphism where its inverse is also primitive recursive, right? So these are going to be these things where you can have these degrees that contain, okay, I mean, I guess the spoiler, because otherwise we wouldn't be making this definition, is that these exist, right? So we can get in the same degree things that are not punctually isomorphic, and this is what I'm calling an outlier. So it's one of these presentations where there's something in the same degree, but they're not punctually isomorphic. And so this was done by one of Sasha's master's students, and he got a few examples. and more recently I've been working with him. Again, of course, I'm going back to the linear orders to kind of find some examples that have these outliers. So this is mostly to show that these exist. And moreover, now we have this quite a new theorem that tells us that every degree is going to contain exactly one punctual structure or infinitely many. So in each degree, you either have infinitely many outliers or you're going to have no outliers. And so finally, what happened to my other slide? That's okay. That's okay. I remember the question. But we'll also talk about these open questions. For outliers, we can, again, there are many open questions here because this was quite recently looked at. So for example, it would be nice if we have some characterization for like what gives this property. Of course, starting with like natural classes, personally, like I really like the linear orders. So I'm trying to think, in linear orders, can we characterize when these exist or not? And obviously it would be nice to do this in general or for more classes of structures. Another question is whether when you have a single punctual degree, so you have something, basically, yeah, you have everything is in the same degree, right? So you can always do this in each direction. Does this make it punctually categorical? And this would be a very interesting question to answer. It is true for finitely generated structures, then you get that it's punctually categorical, but it's still open for every other structure. So there's plenty of things open there. And before I finish, I wanted to state my other open question, which disappeared accidentally. Clearly, I deleted that slide at some point, is that going sort of back to what we kind of have about punctual dimension. As I said, right, punctually categorical things can be very complicated in the computable sense. So a particular question I'm very interested in is whether we can combine the combined punctual dimension, finite punctual dimension and computable dimension, right? To get, does there exist a structure with punctual dimension n and computable dimension m for any n and m, or maybe there's some reliance, there's no obvious blockages for why this can't be true. For example, the finite punctual dimension things here are all computably categorical. So we can get sort of n and 1, but we can also get the example of the thing that is punctually categorical but not computably categorical has punctual dimension 1 and computable dimension infinity. And then the question is, what other combinations can we come up with? And again, the techniques for these two proofs are very, very different. So this would be a hard question to answer, but it would be very interesting because then we kind of really can see more of how these things really relate, because they're somewhat surprisingly disjoint from each other. Okay, I think that is all I wanted to say. So thank you.